All right, this is a debriefing on a homework assignment where you were to practice doing some scale calculations. The assignment said for a circular orbit around the Earth, a geosynchronous satellite has a period of 23 hours, 56 minutes, 4.091 seconds. Given that period, calculate the orbital radius r and give the answer in units of kilometers. All right, well, so for problem 1, part A, the central body is the Earth, and the period is 23 hours, 56 minutes, 4.091 seconds. You need to convert that all into units of seconds, which would be 23 hours times 3,600 seconds, plus 56 minutes times 60 seconds per minute, plus 4.091 seconds yields period T of 86,164.091 seconds is the length of one sidereal day on Earth. I need to calculate the orbit radius. T squared equals 4 pi squared r cubed divided by g divided by m. So r is equal to the cube root of gmt squared divided by 4 pi squared. Well, open parentheses. Actually, first let me show you. So I have 6.672 times 10 to the negative 11 Newton meters squared per kilogram squared stored as g on my calculator, and I have the mass of the Earth is 5.974 times 10 to the 24th power kilograms. So to find r, I would go open parentheses, g, m, and then the period, which was 86164.091 squared, divide by 4, divide by pi squared, close parentheses, raised to the 3 to the inverse 1 power, like this, enter. So there is the orbit radius in units of meters. 42,163,600 meters. And if I divide it by 1,000, I will have converted it into units of kilometers. So the answer to part A, the orbit radius would be 42,164 kilometers. And even that is to 5 significant digits. It's good enough for what we're doing. Part B, draw a circle of radius r to scale on a sheet of paper. Well, a sheet of paper is 8.5 by 11 inches, and I want to use a metric scale for that. So I want a scale that will fit this circle on the paper. I don't really want to go much beyond about 20 centimeters of diameter. So it fits on the narrow side of the sheet of paper. So if I divide 42 by 20, that would be like 2,000. Actually, I'm sorry, I'd have to divide it by half of that. If 20 is my maximum diameter in centimeters, then 10 would be my maximum radius in centimeters. And that means I should be doing about 40,000 kilometers per 10 centimeters, right? So I should be doing about 4,000 kilometers per centimeter. That's one option. Philosophically, I used to encourage you to do everything in ratios of factors of 1 or 2 or 5. So if I were to use a scale where 1 centimeter is equal to 5,000 kilometers, then 42,164 divided by 5,000 yields 8.4 centimeters, which is less than the 10 or 10 point something centimeters I wanted to limit myself to. So that will fit. I will go ahead and use a scale of 1 centimeter is 5,000 kilometers. So on this scale, maybe I should write this down then. So on this scale, part B, the scaled radius is going to be 8.4, and if I can do it, 3 centimeters will be the radius of the Earth on the scale. Well, for the diameter then, if I were to double that, I have 16.9 centimeters. So maybe I should just pick a point on this sheet of paper, and I see if I'm really careful, I can have it fit on my remaining sheet of paper. If I go from here to there, that's 16.9 centimeters, which you can't quite see unless I zoom out completely. So 0 to 16.9 centimeters. And if I go something like this, oh heck, let's see where the halfway point is. Halfway would be 8.43, which would put it about here. So along this line, if I go 8.5 in both sides, and I say, here's one edge, and 16.9 puts it there. So very crudely, and I'm terrible at drawing circles, right? But one of my better attempts anyways. Well, everyone knows the Earth isn't perfectly spherical anyways. Yes! Try not to laugh too much. So crudely, I suppose I could slightly erase the worst parts of it. Here is the Earth to some sort of scale. I'm sorry. This is the orbit of geosynchronous orbit to some sort of scale here. Great. So my scale choice was centimeter is 5,000 kilometers. And this is an excellent drawing of geosynchronous orbit. Look at this practically perfect circle. Part C, add the Earth to scale. Well, in case you have forgotten, the radius of the Earth is 6,378.14 kilometers, average radius used by the program called SPK. And if I take 6,378 and I divide it by 5,000, I have a radius of 1.28 centimeters. 1.28 centimeters to scale. If I double that to get a diameter, I have a diameter for the Earth on the scale of 2.55 centimeters. So now I'm going to try to add that to this drawing to that sort of scale. Ha! It's about 1 inch in diameter, right? So my numbers say 1.28, puts it around here, to 2.55, puts it about there. And I could go this way as well. Not a very great job. Yes, so there's the Earth, a little misshapen. Oh well, continental drift taking place, no doubt, right there. That's a joke. Okay, so here's the Earth, it's crudely to scale, geosynchronous orbit, end of part one. Number two, the International Space Station orbits at an altitude of 410 kilometers. Calculate the orbital speed for the ISS, noting that the orbital radius is the sum of the planetary radius plus the orbital altitude. So as far as calculations go, you would say R is equal to 6378 kilometers plus 410 kilometers yields 6,788 kilometers. And you're going to be solving for the orbit speed. So orbit speed is the square root of gm over r, where r is in meters. So on my calculator, square root of gm over 6788000, so that you have kilometers converted to meters correctly like you're supposed to. And I'll autofocus and I'll press the enter key. There's the answer. 7,660 meters per second. And this will be problem 2, part A. 7,660 meters per second to 3 sig figs is good enough. Scribbled here. 7,660 meters per second. Part B, add the ISS orbit to scale. Well, okay, so it's 410 kilometers. If I take the orbit radius of 6788 and divide that by 5,000 kilometers per centimeter, the radius of the ISS would be 1.36 centimeters. Doubling that means the diameter of the ISS orbit should be 2.72 centimeters. And you can't really be that precise when you're drawing it the way I am, right? So 1.36 centimeters makes it about like that. And 2.72 makes it about like that. So basically put a very thin ring around the Earth. And this is the farthest that any human has traveled throughout the universe in your lifetime. A little thin ring around planet Earth. No human in your lifetime has been to geosynchronous orbit. No human in your lifetime has been halfway to geosynchronous orbit. It just is beyond the range of human travel in your lifetime. Great. Now, number 3, global positioning satellite system. Satellites have a period of 11 hours, 58 minutes. Part A, calculate the orbit radius r. Well, okay. Same formula. I'm solving for r. So on my calculator, I'm going to open parentheses and go G, M, and for the period, what I can do is go open parentheses and type in 11 times 3,600 plus 58 times 60, close parentheses, and that gives me the number of seconds in 11 hours and 58 minutes. Now this is the orbital period in seconds, so finally I can square it. Now divide that numerator by, if you like, you can do it with open parentheses, 4 times pi squared, close parentheses, and now all of that is in the denominator. Close the outermost parentheses and raise this entire expression to 3 to the negative first power, which means to the 1/3 power, or take the cube root. Boop. There's the answer in units of meters. So for problem 3, part A, the orbit radius is this. However, I tend to express things in kilometers, not meters. So I'm going to choose to divide this by 1,000 and say the orbital radius is 26,560 kilometers. 26,560 kilometers, or if you make it 600 kilometers instead, okay, I'll be able to grade it anyways, right? So that is the answer to part A. Part B, add the GPS orbit to scale. Well, my scale is 1 centimeter on my paper represents 5,000 kilometers. So if I take this orbit radius of 26,560 kilometers and I divide it by 5,000 centimeters per, kilometers per centimeter, then to scale, I have a radius of 5.31 centimeters. Doubling that, my diameter would be 10.6 centimeters. Something I can finally measure to scale and be reasonably close in what I'm trying to do. So I'm going to make this approximately go from here to there. There's 10.6. And from about here to about there. And more excellent circle drawing skills by me. Oh, wow, look at this nearly perfect circle I'm drawing again. Practically perfect, as Mary Poppins would probably say. Ta-da! Another expertly, practically perfect circle drawn by Mr. Turek, illustrating the relative scale of the Earth, the International Space Station, the farthest humans have gone from the Earth in your lifetime, the orbital location of the geo positioning satellite system, and geosynchronous orbit. Also, wow, the top of my head is a distraction for sure. Okay, geosynchronous orbit. And geostationary orbit is a subset of that. Okay, so finally, number 4. Calculate the distance from the center of the Earth to the center of the Moon using your scale from the previous problems. Don't attempt to draw it. For number 4, we look up the distance from the center of the Earth to the center of the Moon, and we see that distance is 384,400 kilometers in real life. To figure out what the scale is, we take that number, 384,400, and divide it by our scale factor of 5,000 kilometers per centimeter, and beep, 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 I get an orbit radius of 76.9 centimeters. Doubling that means the diameter would be 150, call it 4 centimeters, which is 1.5 meters in diameter. This is 3/4 of a meter in radius on this scale. If you want to think of that in terms of inches, the 76.9 centimeters corresponds to 30 inches, 30.3 inches. As a little add-on, I have used Autodesk Inventor Pro to draw the circles neatly to scale. Here is the Earth, and to scale is the orbit of the International Space Station. As you can see, it is just a tiny fraction of the Earth's radius above the surface of the Earth. It's above the Earth's atmosphere, but not by a lot. 410 kilometers does not take you very far into space. GPS is for the Global Positioning Satellite System that we use for navigating on cars and boats and military and civilian vehicles. And out from that is geosynchronous orbit. Oh, sorry, didn't mean to actually write on this. Which is where satellites orbit the Earth in one day. All right, now you can see it to scale.